Let's remind what we have done and what we'll be doing. We are analyzing the second order circuits. Second order circuit, we found the mathematical model and we find the mathematical solution as we have done it in the analysis in the differential equation course. And then we said there is an alternative to this, the physical cases. This alternative includes the natural solution and the forced solution. So we said the first step, we are going to find the natural and forced solutions, parametric ones. All these have got k parameters to be calculated. So in this second step, we will be calculating that we found in first step the k parameters. So in order to calculate the k parameters, this is the one that we are going to examine now, we need numerical values, because these numerical values determines the characteristic root. Characteristic root determine the our output functions. The format of these functions will change. Therefore, we need numerical values. For different numerical values, different real roots that we are going to have. So the first thing we do for the real roots, so this part for natural and forced solutions, these are we have already done. These are the first step what we have found. We found the k parameters here. We found the k parameters here. Now how we are going to calculate these k parameters for the natural solution and for the given circuit. So if you go into the details of the calculation, these are the numerical values. These numerical values are critical because if you give these numerical values, you're going to end up with a real root. So if you, this is the characteristic equation, these are the characteristic roots. I am not repeating these calculations step by step because this is the same as we have done it for the mathematical solution. So you end up with a solution like that. Now the difference between the mathematical solution and this solution appears here, because in the mathematical solution we said in order to calculate the k values, you've got to calculate the particular solution and then use the initial conditions to find the k values. In here, we are trying to find out the natural solution. Natural solution is a circuit, and in this circuit there is no any particular solution, because in this circuit we do not have any independent source. So we will be calculating the k values here directly by using the initial conditions without calculating particular solution and finding the general solution. The second step, we are going to calculate these k values. How we are going to calculate it? First, we are finding the initial condition of the derivatives. How we found it? From this equation we can find it. If you put the initial conditions here, you're going to find the initial conditions of the derivatives. If you do the calculation, you end up with these values. And if you apply, then you've got 4 unknowns, 4 equations that you can find. But it doesn't mean that you're going to choose 4 equations, 4 unknowns. We are going to divide it in 2. How we do it? So in here, VCT function, k11 e to the power minus 5000t plus k1 to the e to the power minus 20,000t. So that's this one. When you replace t with 0, you're going to find an equation. Because when you replace with 0 here, that's going to be your initial condition. The others, this becomes 1, this becomes 1, so k11, k12. So if you find the derivative of this function and then put t equal to 0. So this is going to be the derivatives initial conditions that you already found here, and another equation here. So this equation and this equations, two equations and two unknowns. These unknowns are k11 and k12. Therefore, I said we are solving two equations, two unknown, and find the VCT. If you do the similar things for the inductor function that you found from here, you end up this result. So k11, k12 has been calculated separately, and this one has been calculated separately. Let's examine the functions, solutions that we found here. This inductor current is this, and the capacitor voltage is changing like that. So we know these are the natural solutions now. When you look at the natural solutions, this solution must go to 0 value. Why is that? Because these solutions are related with the stored energy on the capacitors and inductors. That stored energy is a certain amount of energy. This energy will be absorbed by the circuit, and this energy disappears, because this energy is not a continuous steady energy source that you deliver to the circuit. This is the energy stored on these elements. So this stored energy is going to end up somehow, and it's going to end and become 0. So the currents and voltages become 0, as you see here. And this independent current source current, it starts from that 30 millisecond. So that means there is no jump here. It starts from here. So I said there is no jump. Maybe you might consider that there is a jump here. No, because this is left-hand side here. You've got the initial condition. So this is the energy stored in it. That means initial condition, that current is seen here as a line like that. And it goes up a bit and then disappears exponentially. And this is the voltage now, voltage of the capacitor. It starts from the 12 volts, becomes negative for a while, and then this becomes 0 as well, because the stored energy finished. Now what we have done is natural solution for a real root. So we will be doing it the same thing for the forced solution. Forced solution case means initial conditions are 0 and independent source are in. So here you are. So real roots, we said at the beginning it is real roots. So we're going to use the same element values that we use in the natural case. And then this part is the same, homogeneous solution, characteristic equation, characteristic roots. Now we do not calculate the k values right here as we did it in the natural solution. In here we are going to find a particular solution because we've got independent source in our circuit. So that is the general solution now. Then we are going to calculate these k values. So how we are going to calculate it in details, you could see it here. That is our mathematical model. These are the numerical values, and after the real roots, characteristic roots, our general solution becomes this. So on this I am going to calculate the k values, and I know the initial conditions are 0 since it is the forced solution that we are going to calculate. Initial conditions are 0, and I can calculate the derivatives initial conditions. You see here, you're going to replace t with 0 on the left hand side. It becomes the initial condition of the derivatives. And then since the initial conditions t equals 0 is 0 in this case, this disappears. And that's going to be 1 over c t0. It gives you that value. So derivative initial condition for the capacitor voltage is this, and derivative initial condition for the inductor current is 0. So that means now I have got initial condition, this one equal to 0, 1. Second initial condition for the capacitor, 3, 2. And derivative of the capacitor voltage, 3. And the derivative of the current of the inductor, 4. So I've got 4 knowns, 4 unknowns. I can find out all the k values. But it doesn't mean that 4 variable 4 functions will be solved. We are not going to do it like that. What we are going to do it, from this equation, write this VC and replace t with 0, use the initial condition of the capacitor, you find an equation. If you take the derivative of it and replace t with 0, then you're going to have the derivative initial condition, which is this on the left hand side. And on the k side, on the right hand side, replace t with 0, you're going to end up with another equation. So 2 equations, 2 unknown. From that you can find out the VCT, one of the state variables, resulting function, and the other one you could do it similarly for the inductor. So the curves or graphics that we are going to observe is like that. You see here these graphics, the initial condition starts with 0 because this is the first solution that we are going to calculate. So initial conditions are 0, and these solutions, some of them might disappear, but there are at least some of the solutions which are not 0. Here you are, this current becomes as 1. Why is that? Because there is a DC source that you are applying to the circuit. That means you are delivering energy steadily and continuously to the system. So there should be somewhere current flowing and the voltage difference between terminals. So the next step is the summation of those two. So let me go a bit further. Real roots, find the natural solution, find the first solution, add those up, you're going to get the same solution that you found for the mathematical solution that is given here. That's the mathematical solution. And that is physical solution, natural one, and the forced one. When you add those up, you're going to find this one. So that's end of this video then.